We're really glad to have here Mark Yim from University of Pennsylvania. He's the Asa Whitney Professor of Mechanical Engineering in the School of Engineering and Applied Science at Penn. He's also the director of the GRASP Lab, which is the oldest robotics research laboratory in the country, and it was established in 1980. I remember that I visited that when I was thinking about starting in robotics. It was, an amazing place to be. His group has demonstrated a large range of robots, a humanoid on display at the Philadelphia Museum of Art to transforming robots that can change their shape to the smallest self-powered flying robot in the world. His current research focus includes reconfigurable truss robots that can help in search and rescue operations, swarms of flying robots that can group into shapes that interact with humans, and swarms of microscopic robots that can manufacture materials. He's has done some of the earliest and most innovative work in reconfigurable robotics. And, that was like one of the first things that I started actually learning about and following. His other interests include product design, robotic performance art, novel locomotion, low-cost manipulation, search and rescue, as well as healthcare applications. Prior to Penn, he spent 10 years in industry, including positions at principal scientist at Palo Alto Research Center, formerly Xerox PARC, and Virtual Technologies, a virtual reality startup. He has founded 3 companies and has authored over 50 patents, several of which were awarded over $100 million in litigation. Honors include induction to the National Academy of Inventors, that's a really big deal, MIT's TR100, and the Lindback Award for Distinguished Teaching, which is Penn's highest teaching honor. He got his PhD from Stanford in mechanical engineering under Jean-Claude Latome in computer science, who was like one of the fathers of motion planning. So let's go ahead and welcome Mark.
Thanks, Nancy. Thanks for coming out. For those of you who are here in this, actually it's kind of nice. I mean, seeing the snow out there is kind of amazing. So I'm going to talk about lessons from looking to biology for robots. And this is mostly going to be kind of a retrospective on some of the work that I've done or been involved in. So it's not robots in general. It's, like all of robotics. It's just the stuff that we've done in my lab. So here's an outline. I'm going to talk about modular robotics first, a little bit more on some of the bio-inspired gaits that we've done, some of my older work, and then talk a little bit more about the more recent reconfigurable trusses. Then talk a little bit about snake-like locomotion, and this is going to be looking more at biomimicry as opposed to bio-inspiration. And essentially there's 2 reasons to look at biology. One is for bio-inspiration in terms of improving engineering and what we can do and what we use from biology. And then there's biomimicry, which is usually just to understand what is going on the biology side. Then there's a couple mechanisms that we'll look at for under-actuated swimming and under-actuated flying. And then we're going to end with looking at Amoeba-like robots and Amoeba-sized robots. The latest one is one that I've been most recently working on, and hopefully I'll have time to have more time on that one. Okay, but before we get started, I should tell you a little bit about the GRASP Lab. Since I'm the director of the GRASP Lab, I have to part of my mission is to let the world know about the GRASP Lab. So we have about 21 professors doing robotics in mechanical engineering, computer science, and electrical engineering, all in one space, which is really nice. The robotics is inherently very interdisciplinary, and so having people be able to interact that way is really useful. One of the things that we've also started to do is we have what we call secondary faculty, and so these are people in School of Medicine, School of Nursing, architecture, design, people that are not necessarily directly building robots or doing research for robots, but they're using them, and so they're getting involved. And so that's actually one of the things I found really exciting by coming to this place, is seeing that you've got biologists working with and doing this mind in vitro project with robotics people. Having that type of high diversity is really valuable in terms of making impact and doing interesting research. So that's really good. We have a RoboMasters program with about 200 students, and we have about 130 PhD students. We also have maybe another 100 undergrads that are involved in robotics. They're a little bit more fluid, so we don't write the numbers down there. The other thing that, so this is just taken from our web. This is grasp.upenn.edu, and I'll probably refer to that site again later, just to get more views on the site, and YouTube channel and all that kind of stuff would be nice. So we've got, we are the oldest robotics research lab at 44. We've got, these are the 21 professors doing all kinds of different research, perception, machine learning, control, planning, design, medical robotics, hardware, software. Their faces are there. So let's jump into a little bit more about the talk. First thing I'm going to talk about is modular robotics, or modular and cellular robots. The idea for modular or cellular robots are basically that you have modules that are repeated over and over again, and you can build a robot from all these different parts. Toshi Fukuda in 1990 kind of started this thing which he called CBOT, or cellular robots, and this is kind of a picture of some of the ones that he had. It's really hard to see. I'm sorry, apologize for that. But he also had this picture, I just made this one up myself, but he had a picture something like this, where theoretically he said you could maybe make these cellular robots really small, inject them into your bloodstream, and have them assemble into your heart, and it could repair a human heart. So that thing, when he started saying that, was basically, people started talking about this type of idea of injecting robots into people's bodies to do stuff for a long time, and I think it got a little bit, overhyped to some extent, especially when MEMS technology started coming into play. And so there are a lot of people doing things along these lines of injecting small micro robots, but not in this fashion. The idea basically is that you could have robots that could assemble themselves, and you have a bigger robot system. So here are a couple of the ones that I've had that you can arrange in different ways to do different things. The main thing to remember is that each module has computation, actuation, and sensing all incorporated into itself. Each module can do something by themselves, but not very much, and it becomes much more capable as you add more of them together. So let me just show you a couple examples for locomotion. Here's maybe 6 modules kind of hopping around. These are another set of modules that you can roll like a loop, again, doing different types of locomotion. It can also transform itself, open up, and move like a snake. I'll talk a little bit more about snake-like locomotion. You could have a little 4-legged locomotion. This is actually taking a snake-like form, and we put it in a gopher hole outside of, this is when I was at Xerox PARC. The gate that it uses inside that hole is called a concertina gate, which actually this is blind, and there's no force sensing or anything. It's just moving in a certain pattern and eventually be able to make that sharp angle. It can also do a variety of climbing. So here it's climbing up a flagpole if you put the right attachments on the robot. It can also climb fences if you, again, attach little hooks onto the robot. Climb stairs. In this particular gate, it's conforming to the shape of the stair, and that one works quite well. This one is also interesting in that it's using human-like equipment, but it's not in a human form, which I think is important. You don't necessarily need to be in the human form to use human equipment. A lot of times people talk about humanoids really important because you want the humanoid robot to be able to use human equipment, but that's actually not necessary. So this is what we call a 14-legged centipede gait. Sometimes I hear biologists say, it's not a centipede, it doesn't have 100 legs. I mean, centipedes don't have 100 legs either, but in any case, this only has 14 legs. The significance of this particular gate is that it's the largest number of modules that we put together in a single system that could actually do something. So it's can kind of walk, and we'll talk a little bit more about that later as well. All right, so we can do a lot of different things, and we've done hundreds of different gates. One of the things that when you have this type of robot, you could say, oh, it's kind of like Legos. You can build anything, depending on what you want to do. And one of the things that people often say is if you need a larger workspace, if you need the robot to have a larger reach, add more modules, you can make longer arms and increase your workspace. If you need more strength, you could theoretically add more modules, put modules in parallel. They can distribute the weight or the forces for whatever you want to do. If you wanted more versatility, add more modules. The number of configurations grows exponentially in terms of the type of combinations that you can do with them. So you have more modules, you can do more things. In reality, doesn't quite work out so well. When you have a larger workspace, it turns out you need larger strength. There's something we call characteristic strength, the number of modules that a robot can support against gravity in a cantilever form. And usually that characteristic strength of modules like we built is around 3 or 4, or sometimes 5 or 6. And that's it. You can't, if you add more, the one at the shoulder can't support its own weight. So you theoretically could make them stronger by doing things in parallel, but the way we build them, it doesn't work that well. You could theoretically build a soft module that has some type of torque control, so you can actually share the load. The way that people typically build these types of modules is position control, servos, relatively stiff, and so when you put them in parallel, they don't work so well. So it's difficult to put modules to share load. At least no one's done it yet. I think this could be an interesting future project. Maybe we could do something like that in the future. Adding more modules is also kind of difficult. Knowing what shape to be in is actually a difficult thing, and that in itself is an interesting problem. Maybe someone could get a thesis on that. Also, the more modules you have, the more likely that one of them will fail. And so half of the problem is making things robust in a way that can make things not robust to that type of failure. Yeah.
So I have a question. It seems to me like, like tug of war is an example where you would have a whole bunch more modules and you should have more strength. Why doesn't something like that work here?
Okay, so tug of war is an interesting case. You could have a bunch of modules all together, and the more modules you have, the heavier it is, and so that might be harder to move, but they're not necessarily going to be able to pull. So even if you had all of them sitting on this table in a line, the amount of force that it could pull with are, assuming that they're not going to slip, are probably just the ones in the front. The ones in the back don't necessarily add to the force that you can pull on. Forces don't necessarily add up together. It depends on the situation. So it's if they are compliant in a sense where load can be shared, then it can work. But in most of the ones that we've built, they don't built that way. Okay, so here is an example of a new type of more biologically inspired gait. In this particular one, there was this sample I showed earlier. It's just the spine of the body that's articulated. And so it kind of moves maybe like a salamander or other type of lizard, but it's also dynamic. The legs are springy, so it's bouncing as it goes. This is a version of that didn't quite work so well. So at this point, we're experimenting with different lengths and stiffnesses of the legs that were passive. And it kind of bounces around, but maybe it's too high. And so what's the right speed? What's the right stiffness? How do you do that? There's a lot of optimization that you could do on this. So one of my students worked with Dan Kodacek on Rex. This is a very old, famous robot called RHEX, Rex, with 6 legs that are also somewhat springy. And this actually came about with how many of you have heard of Rex? Have any of you heard of Rex? Couple? Okay, so for those of you who haven't heard of Rex, this is kind of really cool. Dan Kodacek worked with Bob Full out at Berkeley several decades ago, and they looked at cockroaches, and they were looking at how does a cockroach climb over obstacles really, really well. And when they did these high-speed video and analyze it, a cockroach doesn't think about where it's pushing each foot as it goes. It just swings its leg wildly, and it climbs over obstacles, and it just works. It just bounces over things really, really well. And so they realized they could do kind of the same thing. If you have the right motion with the legs, with a little bit of springiness, it just goes over unstructured terrain really, really well. And Rex was one of the examples. So one of the things that was kind of interesting that they did with this was, how do you find out what the right springiness is? And they spent a little bit of time trying to come up with optimizing the gait, optimizing the stiffness. They had changing stiffness legs, all this kind of stuff. And so Kevin Galloway, my student, worked with Dan on, they used the optimization Elder-Mead technique. They went through maybe hundreds of physical trials and then thousands of simulated trials and something like that. And they got something to work pretty well. So I want to make a little plug for GRASP here. Just last week, we had Jitendra Malik from Berkeley give a talk in our robotic seminar series. It's on YouTube, so check out our YouTube channel. Try to get our clicks up a little bit there. In this talk, one of the things that he showed was a quadruped doing, again, essentially gait optimization, walking around and using a learning technique. So one of the things he said one of the things they showed was that this robot, they could get the robot to walk slowly, and as they speeded it up, it will naturally transition to a trot gait, could go over different types of terrain, all kinds of things. That was pretty amazing. And the interesting thing one of the things I found interesting was that he talked about what enabled this to happen, as opposed to what happened 10, 15 years ago. Instead of having thousands of trials in this optimized gait or using learning techniques, they could have large data sets that fed their model, and then instead of thousands, they had 100 million iterations. They have now the compute power and the resources to do that type of thing, and once you have that, you can have much greater performance, which is kind of interesting. Okay, so this is basically the structure I'm going to have. I'm going to talk a little bit about some robots, and then have a slide on like what did we learn from biology. So this kind of my take on working with modular robots and doing a bunch of different gaits over the past couple decades. So we've done 100 different configurations. Most of the time, most of the configurations that we had less than 12 modules. Usually it's like 5 or 6. The largest number of modules we had was the centipede gait with 45 modules. And that was kind of like just because we wanted to see how many modules we could put on a robot. How it worked was actually not very good. I mean, it could move in a straight line, kind of, not that great. And so one of the things that I took away from this, essentially looking at these, somewhat biologically inspired locomotion gaits, is that in general, more modules led to worse performance. Essentially, what you want to do is match the number of, it's like an impedance match in electronics. You want to have the right complexity, the right number of modules or degrees of freedom that fits the complexity of the task. So one fallacy maybe, and when you think about modular or cellular robots, is that like cells, you have in your body, you have what is it, billions of cells or something, but only hundreds of types of cells. But there are lots and lots of cells. It's not the same thing when you think about a modular approach. In our case, our modules have, actuators, sensors, computers all together, and it has each one has some functionality. So it's modular in that sense, and you can put them together, but it's not like cells where you can just add a bunch of them and they work well in that sense. So one way to think about it may be the granularity of modularity that's applied. Okay, so another thing when we think about modules is this particular gait where we had the tricycle and the modules on it moving. This is another thing where it kind of worked. We got the video, but it didn't work that well. There are something like 20 modules on here. You only need like maybe 2 or 3 degrees of freedom, but we've got 20 degrees of freedom, right? 20 motors, and essentially every module here is like a muscle. And in that sense, it's kind of like an octopus. So having all of the same type of module is not necessarily a good thing. Octopi they are really amazing, amazing animals. They can squeeze through areas. They have very, very good ability to move around and do things like that. But they're really bad at lifting things. They're really bad at, imagine, you know, so they have no bones. So imagine I'm standing here and all my bones were gone. What would it be? I would be a puddle of flesh on the ground. I wouldn't be able to move. I wouldn't be able to stand or walk. Bones can be really useful when you want to do things like apply forces, large forces and torques in an environment. So looking at that got us to think about, well, maybe we shouldn't have modules in the sense like we've done in the past. And that got us to start. The thing that I'm working on now, it's a little bit more recent, and an area that I think scales better is something we call truss robots, or this is called a variable topology truss. And essentially, what it's doing now is also what in the past have been called a variable geometry truss. So it's a truss where each link can change its length. And you can do things like this. You can walk around, tumble, that type of thing. There are much more interesting computational issues with this particular robot system. So this is, you know, you can have arbitrary structures. This just shows a picture of how you might represent the nodes and the edges of a graph. You can represent it as a graph. This particular system also can change its topology. So it can rearrange the assembled nodes and truss members. So here's a typical motion planning problem that we have with a truss. We have a truss in this shape and another truss in this shape. You have to have the same number of nodes and edges. Is it possible for this guy to go into that shape without self-collision? And it turns out that self-collision is a really difficult thing to deal with a truss robot with this many members, because it happens all the time. Anytime you move, it's very likely that your members will collide together. It turns out in this particular, actually, let's just take it. How many people think that this can? Does anyone think that this can go from this one to the other one? Just by looking at it. I mean, there's no real note, but if you just want to guess. All right, so a third, fourth, that's good. So it turns out it can. Let's see if I can get this video to go. Okay, so this is the motion that the nodes and the members have to go through to do it without colliding. So this is fairly convoluted, and my student had to work pretty hard to find a way to get it to be this complicated. It turns out that for a truss that looks like this, it's rare that you can have something that, you know, drastic in terms of motions. It turns out that if you look at the C-space, there are 25,000 disconnected regions. The collision happens a lot. And so given two arbitrary configurations, it's like less than 3% chance that you have a path between the two without collision. So the one thing from a biological inspiration point, we actually looked at DNA. So there's this thing called Topoisomerase, this little enzyme that when a DNA molecule replicates, this enzyme comes in and it actually breaks apart the DNA chain and then reassembles it. The thing, they have these things where they get coiled up. The DNA molecules get coiled up a lot, and in order to replicate, they need to uncoil. And so there's this thing that just comes in and breaks it apart and uncoils it and then reassembles it, and it works. Of course, it works. People have their replication all the time, so it's kind of amazing. We have a paper on how we can do kind of the same thing with our system. In this particular case, this diagonal element is in the way. It's impossible for the robot to move from one configuration to the other without bumping into this particular bar. But if you split in two, you can actually move around that one and then reassemble on the other side. So based on that, it kind of we can get the help to do the self-reconfiguration and motion planning problem. The other thing another tool that my student Alexander Spinos came up with is inspired by knot theory. So one of the things you want to, if you look at a really complex configuration, essentially if you want to determine whether you can move from one place to another without collision, is to look at the different links, the closed chains. So here we have one closed chain, another closed chain, and another closed chain, and actually this different combination of closed chains, and some that are linked together. If you needed it to break out of it, you can't without reconfiguring, without breaking open the nodes. So using what's called a spatial graph, which is linked, which is kind of a derivative of from knot theory, you can have a 2D picture where this is the crossovers are shown in 3D by showing a gap on one side or the other. You can decompose this graph by looking at the different closed chains, and so in this case there are 3 different combinations, and then from these 3, you know that okay, these 2 are linked together, these 2 are linked together, these 2 are not linked, and then by attaching to the original graph this linked, not linked set, we come up with what we call this augmented graph. And if you take the augmented graph representation of the initial and your final form to check to see whether they can come together, you just check to see whether this linked augmented graph is isomorphic with each other. And if they are not isomorphic, then there is no collision-free path. They will collide. You must reconfigure. So this is relatively fast. We use the Brendan McKay's NAUTI to check for the isomorphism, and it speeds up the reconfiguration process and just the analysis very, very quickly. Turns out that if you have a small number of links, there are not that many number of invariants. There's only 4 different isomorphic shapes. But once you get to something more complex, it grows exponentially. There are over 25,000 different. One way to think about it is like connected components within this configuration space. Okay, so looking to biology, it's historically it's kind of interesting. A lot of motion planning techniques have been used for drug design. You can look at molecules and see how they move around by using some of the high dimension motion planning techniques. My old advisor did a lot of that. Here, we're actually using complex molecule mechanisms, or at least thinking about this, the Topoisomerase, to inspire reconfiguration planning, so kind of doing things in reverse. It's kind of an interesting aspect. Any questions on that before we move on to snake locomotion? Okay. Oh yeah, question.
Can you maybe go back to the last slide? The one more. So in this case, if you're around 500, your chances are actually lower than the 2000 case.
Yeah, I don't know why that is.
Okay.
Yeah.
Maybe it depends on how you initialize your trust or something.
So I'm not sure. My guess is that it could be the number of invariants isn't necessary. You may have a really big one, and then lots and lots of tiny ones, in which case the probability of finding a connection is higher than if you have evenly distributed, small ones.
Okay, thank you.
Any other questions?
Okay. Good question. I wish my student was here to answer for real. Okay, snake locomotion. There are essentially 5 different types of ways that snakes move. There's something that's called rectilinear undulation, which is kind of this one, which is undulating in the vertical axis. This one is concertina. The one that's there's 2 others, slide pushing and push points, which I'll get to in a moment, but the most popular one that people usually think about snakes is lateral undulation. So this is lateral undulation. Snakes are moving in the horizontal plane. It's undulating in the horizontal plane. This is actually a video that David Hughes is a very interesting biologist at Georgia Tech, who's shown me some of these things. So there's a lot of studies of lateral undulation. So if you take that motion and you get a robot to do that motion, this is what happens. So in a naive way, we have a modular system with, I think it's 4 or 5 modules in the plane. It doesn't move properly. It doesn't move like a snake. It doesn't make any forward progress. It just sits there wiggling in place. So one of the things that might be the case is something that's called differential friction. If you put wheels on a robot and you make the same motion, it works really well. It moves very much like a snake moves. So the problem here is that snakes don't have wheels. So why is it that snakes can move and the robot can't? So this I just found this on YouTube. It's some random guy with a pet snake who decided to videotape it. This one, the floor is kind of slick. So this snake is not actually using that type of motion either. It's something that's called slide pushing. It kind of bunches its body up and then sticks out a little bit more. But here's something really interesting. The snake very attentively went to that particular post and then wrapped its body around it in order to push against that post. So that's what's called push points. They use the environment, vertical features in the environment to push against in order to make progress. So there have been people that use this type of push. They've done studies on snake robots that do the same type of thing. This one's a really funny one. I'm not sure why this snake was doing this. It's a very slick thing, and it's not making progress, obviously, and it's not using those other 2 techniques either. But so there is a thing called sinus lifting, which is a way that that a snake can move, and that's what's happening here. We've added the ability to move in the vertical plane as well as the horizontal plane. So if you notice here, this part of the robot and this part of the robot and this part of the robot is not touching the ground. The only parts are on these 2 parts. And if you look at a real snake here, you can see it's doing the same thing. There, the parts are above the ground. It's part of the robot is up and part are not, and that's how it actually makes progress. One of the things that's funny about this particular gate is that we have these wires in the back. That's because as it was moving, it wouldn't always go straight. It tended to kind of wander or oscillate or turn in funny ways, and that's kind of a problem. And then when we looked at this video, actually the snake is kind of doing the same thing. It's kind of like wandering around, and maybe that's just how it does it. Okay, so this is biomimicry. It's just trying to copy biology, and so what can the robots teach us about biology? And essentially, for lateral undulation, it seems like there are 2 major mechanisms. There's differential friction, and there's this sinus lifting. There have been studies on the snake skin where they did notice that under a microscope, they have these little features which give them friction in one way is different than friction side to side. And so that does actually work to some extent, but probably it's some combination of 2 for most cases. Just so one other kind of side topic for all of you PhD students, this particular stuff that I'm showing you here is work that we put 2 or 3 years of work into this and then didn't publish because it turned out that someone else had published it like months before we did. So, that's just one incentive, publish things early because they can bad thing. Well, you'd like to get credit. So that's why I'm also, you don't always get a chance. I'm talking about it now because I was not able to publish it either. But anyway, it's fun stuff to do. All right, any questions on that before we go to this 3rd topic? Okay, under-actuated swimming and under-actuated flying. So the first thing is this, another project where we have what we call mod boats. These are boats that can form larger structures in water. So they have magnets on the sides, and they can if they get close enough to each other, they can dock by using the magnets. They can also swim together. Doing the control was one of the big things. How can you get them to move together in a coordinated fashion? In order to dock, you need to have fairly precise motion to get close enough to dock. And so we had to figure out how to get them to move together. This particular, so this is the bottom side of what it actually looks like. And this is where it kind of looks like a turtle swimming to some extent. Essentially what happens is the design is one motor. So that's why it's underactuated. And then there are these passive flippers that as the motor just twists the thing back and forth, the flippers flip out and grab the water to make progress. So this was actually designed by Raphael and Degani a while ago, which we thought was a really cool design. So we copied the design and then built on it. So one of the ways of steering with this thing is essentially you can model the forward progress as sinusoids or a cosine function, an amplitude and a cosine function. If you want to steer it, the way that Raphael and Degani did and the way we implemented was to change the speed that it's moving. So this represents just the angle. And so this is the sinusoid, the angle as it rotates back and forth. And one side is like the left flipper and the other side is the right flipper. And by changing the speed of either the left flipper or the right flipper, you get this type of motion here. This one's faster on, let's say, the right flipper. And so this orange section is turning one way and the yellow section is turning the other way. And that works, kind of. So it's also fairly straightforward. You know, if you look at this equation for equation of motion of how we're controlling it to move, the natural thing is to say, okay, we can just change the frequency. It's parameterized in a way where it's easy to change the speed by changing the frequency of the left or right side as you go. Another way to do this is by what we call a pause controller. So instead of changing the speed, we put a pause in the way that it between either after it's moved with the left flipper or after it's moved with the right flipper. This one is a little bit trickier because it's discontinuous, right? The controller is discontinuous. You don't have a single function. But you know, if you think about it, you know, if I'm sitting here swimming along, paddling left and right, and I want to go to the right, I could do this, you know, swim faster with the right, or I could just hit it once and then drift and turn to the left or right. And I think it's a little bit more natural to do it this other way, you know, the pause controller. But so if you look at the way that it actually performed, this is the pause controller, and here it was going to the right, and now it's going vertical, and it just basically made a right angle relatively quickly. This is what we call the frequency modulated steering. It took a long time. It took this big arc. It's much, much slower in order to turn. It's not quite as effective. And in fact, if you do this waypoint following, this blue line is the pause controller. This red line is the frequency one. And here we tried to do a triangle, and the frequency didn't really work very well. Okay, so talk about the results of this in a minute, but basically frequency control didn't work well and the pause controller did. I think the pause controller, to me, seems to make a little bit more sense. We'll get to that in a minute. First, let's talk a little bit about underactuated flying. Has anyone heard about this? You know, the myth that bumblebees shouldn't fly if you use classical aerodynamics. So apparently that there, I don't know. If you look on the internet, supposedly some engineer a long time ago said something like this, that, you know, using normal aerodynamics analysis, bumblebees shouldn't fly. Okay, so part of that thinking, I think, comes from you know, just low Reynolds number, the flow. When you shrink things down, the viscosity ratio of viscous forces to inertial forces changes. And there's another myth that insect-sized propellers can't work because they're too inefficient at that scale. And so as you shrink propellers smaller and smaller, you need to go to this flapping wing like insects do. And there's a lot of research now. A lot of people have been trying to get insect level flying, and they've been looking at flapping, and there's all kinds of really cool stuff looking at the vortex shedding in order to increase the efficiency of flying, and they've got a lot of things flying with flapping wings, even at the small level. So I talked to this guy, David Lentink. I forget, he used to be at Stanford. I think he's at Duke now. Anyway, he's at a different place now, but he basically studied these things, and he said, actually, no, propellers will work at a much smaller level. And so we did this a while ago, 5 years ago. We developed this is now the smallest flying drone in the world. It's at about 3 centimeters, self-powered. It has its own batteries. There are other people who've done things without batteries, but they're tethered, and so I don't think that counts. And it has a propeller. It doesn't have a flapping wing. One of the interesting things is, how does it actually work? It only has one motor. So how do we control it so it can go X, Y, Z? And here's some collaborators at Northwestern, Mike Rubenstein and his students. We can do station keeping. We can do step responses vertically, horizontally. The light you see there is on the edge, the little LED that's showing when it works by pulsing the propellers, and the light shows when it's propulsing at different points in the rotation. So how does it work? This is kind of a close-up version of the system. There's a motor with a small propeller. It's a white propeller here. This kind of shows the axis of the motor. It's not in the center of the robot. The center of mass is actually offset. So because it's offset, the motor is also spinning in addition to the propeller spinning. What we can do is we can pulse the motor at different points depending on where it is in the rotation, and that will cause a moment, which will lead to a angular velocity. So we can control the roll or pitch or the attitude of the vehicle as it's flying, and that's how we control its XY position. So one of the things that actually took a long time to figure out and to get right was the distribution of the masses. So it turns out that one way to think of it, it's not exactly what we did, but you can kind of think of it like a maple seed or Samara. In order to get passive stability, like when a maple seed falls, it spins in a way that's passively stable. It doesn't fly, crash in a different way. It essentially becomes passively stable. We can use the same type of mechanism by having the masses in the right place. All right, so looking to biology, one of the things that lessons I think we have is don't follow biology blindly. Like, we don't have to have flapping wing vehicles, even at the small side. And the other thing is, don't follow mathematical intuition blindly either. So my student, he did this control law, and he said, okay, we have this parameterization, we want to do control. It's pretty obvious, pretty easy to just change the speed, and then you can get this controller to work. Whereas the pause controller actually, I think, works much better. Okay. Any questions on that? All right, so yeah. Yeah.
What was the claim that something that doesn't have flapping wings cannot fly at that scale? Was that the original claim? All right. Okay, just to clarify. All right, thanks.
Yeah, especially propellers, spinning propellers. Okay, Amoeba-like locomotion and Amoeba-sized locomotion. So here's this work on essentially looking at the way that amoebas move, which is kind of like you can see material from the backside squeezing out the front side, and that's the way it kind of moves around. It kind of oozes. And there's a thing that's, I think it's called the water wiggly. It's a little toy, it's a little toroid that's filled with water, and as you push one side, material will go through the middle and out the front. So essentially what we did was Dennis Hong and I and one of his students, we came up with the way of chemically inducing swelling so that we can get that same type of motion. So here, applying a certain type of, I think it was hexane or something on the backside of a polymer, and you can get the robot to shrink, change its stresses on one side. And we wrote a proposal to DARPA for the ChemBots project, where we would essentially have some way of chemically getting this thing to move by applying chemicals to the right places. It didn't work that well. We could get it to move once, but the chemical stuff didn't really work that well. There is another robot system that also uses what we call eversion, and this is the Vine robot. So Elliot Hawks and Alison Okamura and her students came up with this idea where you have a bunch of material, plastic material, inside the robot, and it squeezes out the front part, and you can get this thing to grow out the front end and squeeze through tight areas, and it works really well. So there are probably 4 or 5 groups around the world that are pushing this idea. It can go over long distances. It can also apply, if you get it to squeeze under some object and then pressurize it, you can actually have large forces to lift it up as well. Steering at the front, steering of this thing that's growing out is not that easy. You can do it, it's not that easy. Applying forces, arbitrary forces, you'd like to think of it as like a long robot arm, but getting forces out at the tip is not that clear either. But it is kind of an interesting system that uses the same mechanism that's like an amoeba that works really well. Okay, so the last part of this talk, I'm going to talk about this new work. We just submitted a paper on IROS deadline was a couple days ago. So we just submitted, this is not published yet, but it's, I think, really fun. So I'm going to talk about it here. Mark Miskin is a professor at GRASP, an assistant professor there, and he did this work while he was I think he was still a PhD student at Cornell, where he had, this is 70 microns across, so it's microscopic. And it's in water, so it's submerged, and it's walking. It's got these little legs. This little white light you see, this dot, is essentially its power source. It's shining light on little solar panels, and that's getting it to walk. So essentially what he did is he solved 2 problems that were, for all the people trying to do micro robot development, making teeny tiny actuators, little tiny motors, was difficult. He came up with this thing, which are essentially these little electrochemically actuated. You apply a voltage and current to this material and it bends. And then he also solved the power problem. The other big problem is power, and he does that just by shining light. The actuators take very small amount of energy, and so you can get this thing to work. So this is so one of the problems with this is this type of video is the bulk of the analysis that they had for studying how does it actually work. This is what they thought was happening. They had the robot looking at it from the side, which is really hard to get. I don't know how he got this image, but it's hard to get a side image of this thing because everything's always top down. This is what they thought they had. They would apply voltage to these legs, and they would move. There's front legs and there's back legs, and they would move, and they'd alternate, have the front leg curl and the back leg curl. And it looked like it was working. It was certainly walking. We studied frame by frame each one of the, especially the shadow of where the legs are, and we're pretty sure it's upside down. It's not actually walking the way he thinks it is. In fact, the front legs don't do anything. They're up in the air, and the back legs have curled over. So it's just actuated further than they thought, and every time they shine the light back and forth, the leg is doing this. So because we needed to understand what is actually happening at the microscale, it's too hard. You can't visualize sideways. We developed a large scale model. So this is 1 inch, and we put it in glycerol at 4 degrees. So it's very, very viscous. And this is what we observed. We saw that we could get the robot to move, and we think this is representative of what's happening at the microscale. So what's exciting about this is something that we think we've discovered a 3rd class of locomotion. So normally, when you look at locomotion, there's something called static and dynamic. Static locomotion is statically stable. A hexapod gait, every time you move, it's always statically stable. If it stopped, it wouldn't fall over. Dynamic gaits are what people do normally. Part of your gait, you're falling. This is the dynamic gait. You're falling as you go. Usually you're using inertia. Running is using inertia. It's much more efficient to use inertia. What we have here is dynamic. It's falling, but there's no inertia. Because they're so small, the Reynolds number is so small, we've got viscous forces greatly dominate. The inertial forces are negligible. So it's something we call, this is also, in this particular case, in water or some fluid. So we call it buoyancy-enabled non-inertial dynamic walking. Or at least non-inertial dynamic walking, I think is this weird thing because it's not static and it's not dynamic. It's a third class of locomotion, so we call it BENDY. So if you look here, it moves forward, it moves backwards a little bit, but eventually it makes some progress forward ultimately. And part of the gait is falling. Here it's falling. And it turns out that falling part is critical in terms of making this actually work. So it's, and making forward progress. So we modeled the robot as a single degree of freedom leg that moves back and forth. There's the body. And when you're looking at reciprocating gaits, normally in low Reynolds number flow, when you have something that's reciprocating, it's hard to get anything to make forward progress because every time you move forward, you move backwards, you just stay in the same place. And especially in swimming, if you do this, usually the whole body just waves back and forth and you don't actually make any forward progress. So the ground contact is the thing that's critical in terms of breaking this, what's called kinematic reversibility. And ground contact is modeled by the leg velocity when the leg is moving up and the body's moving down. When the leg is moving up faster than the body's moving down, the leg will lose contact with the ground. How fast the body falls depends on the fluids, and there's something called squeeze flow, which is part of lubrication theory. This purple line here represents squeeze flow, and over time, essentially becomes asymptotic. The closer and closer you get to the ground in squeeze flow, it's harder it is to squeeze that last bit of liquid out, and so it slows down. So if you put that model in, essentially this is what this the simulator shows. This magenta line shows it makes some progress forward and then backward, and then we wait, we pause. During this pause, this kind of green line shows the body falling, and essentially, ultimately you make progress going forward and back, but it works pretty well. So the other thing we can do with this simulator is we can design and optimize what the gait might be. Yeah, question? So I'm not exactly sure about how the scallop theorem, question was scallop theorem.
Yeah, no, I mean, so the scallop theorem is just tells you that if you are in a high viscosity environment, so typically zero inertia, right? Then you cannot have any thrust or any displacement if you don't break symmetry. So if you have the scallop that does like this, that's symmetric, you cannot move anywhere.
Right.
But then the consequence that you need to break symmetry so that you break the reciprocity of the motion.
Yes.
So isn't it this exact same thing?
It's exactly the same thing, yeah. And
Okay.
the ground contact is what breaks the symmetry.
Exactly. So, okay. So it's still, yeah, I was just puzzled by the fact that it's kind of a new mode of locomotion. I thought this, from a fluid dynamics perspective, this is...
So the critical thing here is it's not swimming. This is walking.
No, that's fine. Well, but it's still just one way to break symmetry. You can also do the same, like if you hover over a surface and then you have a boundary effect coming from the wall. That's another way in which you break symmetry and you can move into a viscous flow.
Yeah.
So no, I'm just trying to clarify how this fits with classic fluid mechanics. All right. Okay. Thanks.
Okay. So with this model, one thing we can do is optimize the gait. So here's the old one that we had that's moving at something like a millimeter per second. And it turns out this pause, waiting for the fall, slows the gait down. And in fact, if you change your start and end angle, you can move much faster. So here, there's no pause, and we have a very small, it starts in a certain position, and the legs move much faster, but all at kind of an angle. And you can see it actually moves about 5 times faster than the previous gait. So we can optimize the gait. And then, the real question here is, how does it match with the actual microscopic robot? In this particular case, the way it actually looks like is there's a front end, it's in the air, so theoretically it's not moving, and the back end is what's actually moving back and forth. And we can model that as a rotation. This is much closer to the actual scallop theory. So it's actually, there's an angular velocity of the body, and there's a translation. And so this is the equation that Mark Misson came up with. This first term is the angular velocity, squeeze flow, and the second term is just the moving at an angle. And the second term is kind of interesting because remember the thing is moving back and forth as the leg moves back and forth. And if you're at an angle, the force up is in the opposite sense as the force down because you're moving at this angle. And theoretically, we can exploit that to improve our gait. Modeling what they actually did. This is from Mark's Nature paper. You can see this is the forward progress. It moves forwards and then backwards, and ultimately we make some progress, and we get basically the same type of behavior. So building on that model, we can understand, we know now that the vertical component of the motion is actually really important to understanding how does it move. And so we can start thinking about, what if we have multiple legs? If we've got multiple legs and we can start doing things like turning, which is one thing that most of the micro robot people don't do. They just say, oh, look, we can get the robot to move straight. Okay, but if you actually wanted to get someplace, you probably want to drive it in a certain direction. So having multiple legs, we can start thinking about how do you coordinate its motion that's coupled because of the vertical motion up and down. Lessons from biology, basically this applies to most of everything, I guess, is there are lots of ways to apply biological concepts. Some will work well, like this Vine robot, and some probably won't work so well like we had tried before. Understanding and modeling the micro level behavior of mechanisms is not that easy, but probably important. I think we're at time or past time. Let me just say thanks to all my students that have been involved. A bunch of them are listed here. Oh, actually, one last thing, if it's okay. I wanted to make another pitch for a GRASP. There's a seminar on April 7th. It'll be broadcast on YouTube. All of you should watch on YouTube. It'll be Nancy Amato who will be there. That's right. Yeah. All right. So thanks.